speaker. So maybe I don't know if you want to come down there, Tim. So it's a great pleasure to introduce Tim Taminiau. Tim is a team leader at QTIP in Delft. He is well known for his work on implementations of quantum information processing in solid-state systems, in particular some groundbreaking results that include demonstration of entanglement and fault tolerance in diamond-based quantum processors, some work on loop-hole-free Bell tests, and also work on time crystals recently, and many other very prominent results beside these. And it's a great pleasure to welcome him to Bristol to give our first keynote talk of the conference. So maybe we can get Tim's slides up and get ready to go.
Use that or?
Yeah, I just, well, okay, so.
No mic.
I guess, well, okay, this is the question. So, this is just.
Let's try it, if people can hear me.
Yeah, let's just see if people can hear.
So can people in the back hear me? Okay, yeah? I think it's without amplification, but it's good.
People in here that hear you.
I have no idea. Shall we get started?
Yeah, whenever you're ready, please take it away.
Okay, great. Thanks. Yeah, this looks like it will be an excellent conference. Really looking forward to it. Let's hope the number of fire alarms are limited. Apparently it's a common occurrence here. So in my group, and also clicker doesn't work. No.
Oh, great. Yeah. Hello? Try again?
Yeah.
Okay.
Now it's good. Okay, so an overarching goal of my group and also QTech, the institute where I work, in more general is to build quantum networks. So in that case, we have nodes consisting of multiple qubits that can store and process quantum information. In our case, these will be spin qubits in diamonds. And those nodes can be linked up through photonic channels, so using photons. Now, why do we want to do that? Okay, so why do we want to do that? Motivation here is kind of threefold. So first, these kind of networks can be used for modular or distributed quantum computation, right? So the idea there is that you make little quantum processors and you make a big system by connecting them all together in a modular way using these photonic links. Now, because photons can also travel over long distances, these systems can also be used for quantum cryptography, quantum communication. And finally, one can think of performing a fundamental test of quantum mechanics. Essentially, we haven't really had experimental control yet over these kind of extended large quantum systems. And we can hope to find surprises there, or at least do new tests of quantum mechanics. Now, in this talk, and for this audience, I will focus mostly on this idea of this modular quantum computation, and talk mostly about the quantum information angle and the computation angle. So a bit more about that. What's distributed quantum computation? So what is the general idea here, right? We want to build this kind of network, and the advantage now is that because we have the modular system, where we just have to make small nodes, small processors, and then make many copies of them, there's a kind of inherent scalability to it, right? So this is one way to sidestep the challenge of putting more and more quantum bits on a single chip. Now, second, because these connections are optical, they're flexible and also reconfigurable in real time. And that means you can think of all sorts of topologies. Here, I kind of put a 2D grid. Maybe you recognize this as an idea of building a surface code. But you can also think of three-dimensional systems and connections beyond nearest neighbors. So essentially, any kind of error correction code or architectures you can come up with, you would be able to experimentally test it and then investigate it in these kind of systems. And finally, if you worry about correlated errors, because in principle these distances can be very large, these nodes can be very independent of each other. It's one way also to ensure that at least you don't have correlated errors over the system. Okay, so an example would be, let's say, a grid like this, where you could do something like a service code. This has been beautifully studied by Nickerson et al. From the group of Simon Benjamin. And yeah, just to give you some idea of how that would work is, in the service code, if you have, say, these 9 nodes in this case, you would want to, over these packets, you would want to measure operators like ZZZ or XXX. Now, how would you do that? The idea would be to first distribute a 4-qubit entangled state over 4 of these nodes. And that 4-qubit GHZ state, you can essentially think of it as one ancillary qubit that can perform a non-local stabilizer measurement or parity measurement over those nodes. Right? Showing the diagram here on the right. By doing this, you could measure the XXXX parity. So the idea there is to distribute entanglement and use this as a resource to perform these kind of measurements. Why do we want more qubits per node? Well, one idea can be to have multiple data qubits per node. Right? So here, in the example, it's kind of like 1 qubit of the actual encoding in the service code per node, but you would have more per node. And you can also use additional qubits for things like error detection or entanglement distillation. Because these entangled states are resources, we don't have to deterministically make them. We can do kind of error detection and distillation tricks to get higher fidelities. Okay, let's just a bit of the overarching motivation. And I want to split the rest of the talk up in 3 parts. First, I want to really also just introduce the qubits a little bit and how does it work and what can we do with them. Then I want to show how we can then characterize or study large quantum systems with these qubits. In particular, we'll see how we can characterize about a 45 qubit system. And finally, I want to look into if we can start going into the regime of fault tolerance and encoded qubits by showing that we can encode a logical qubit and operate on it in a fault tolerant way. Okay, let's start at the beginning. First thing we need is a diamond. Right? So qubits are going to be spin qubits in diamond. We don't use natural diamonds. We actually grow these in the lab. Here you see a CVD reactor in the clean room in Delft. If you look through this window, you see here this little diamond, and it's glowing in a plasma. And we're using this as a seed to grow high purity diamonds on top. Sometimes we use our own diamonds, but also often the ones from Element 6 from a company from the UK. One thing that's nice here is that these diamonds have extremely high purity. So we're talking about something like less than a part per billion of impurities. This is really one of the most pure materials that exist and that we can make. The other example that can be made very pure is silicon. Okay, so then in those diamonds we look for defects, and in particular, in this case, we'll consider the nitrogen vacancy defect. It consists of a nitrogen atom that replaces one of the carbon atoms next to a vacancy, a missing carbon atom. This traps some electrons over here, and that forms our qubit. Actually, it's a spin 1 system, so it's a qubit trit. But typically, we tend to just use 2 levels of it as a qubit. Now, what is nice about this system? It's a little bit like an ion that is trapped in a solid. There's very long kind of coherence times, and it also interacts coherently with light, with photons. We then typically work at cryogenic temperatures between 4 and 10 Kelvin. So here you see a very old cryostat. Haven't used it in a long time. Here you see a little diamond. It's wired up on a chip. We zoom in a little bit more. Here, diamonds, a few millimeters large. We zoom in even more in an electron microscope, see these kind of pictures. So the gray stuff here is the diamond. And what we then do is we fabricate these kind of like half spheres called solid immersion lenses that we sculpture out of the diamond using an ion beam. That is really just to get the light out of the diamonds. I have a high reflective index material with a flat surface. I get a lot of total internal reflection. If I make it curved, I exit everywhere perpendicular, I get a lot less reflection, more light comes out. You can see now, indeed, if we now scan a laser over the sample, see here this half sphere, and in the middle is this bright spot. So that's one of these atoms that is fluorescing. And you can see this with your eye. Now we're going to make this kind of like microwave lines all on the sample, and you can send microwave pulses through there, and those are the ones that operate on the spin degree of freedom, so on the actual qubit. Just a very simple example, right? So we can prepare spin in qubit spinning up, apply a microwave pulse of various lengths, and then drive a kind of radio oscillation from up to down and coherently back. See, that can be done pretty fast. 10 nanoseconds in this case for kind of like a Pauli X operation, and with high fidelity. How do we measure the state of the spin? It's very similar as what people do with trapped ions. So at low temperatures, if we put a laser on the defect and we scan the frequency of the laser, and we see these sharp spikes of fluorescence. So this is where we hit and transition from the ground state to the excited state. And because these transitions are spin dependent, we can, for example, turn on a laser that is only resonant with this transition from MSS0 to the excited state, or the MSS0 spin state. So only if we're in this MSS0 spin state, we excite the system, we generate photons, and we see light. Right? So that gives us a readout mechanism to measure the spin state. If we're in the other qubit state, then it stays dark. That's what you can see here. So if we prepare this state, then we detect on average about 8.5 photons. If we prepare the other state, it stays dark, virtually 0 photons. Okay. So what about the kind of coherences in this system? So one thing that's really nice here is that this is a very isolated system. So if you look at the T1, kind of relaxation time, right? So essentially we prepare in one of the 3 eigenstates, and then we just wait and see what happens. Then you see that up here we prepare the states, and if we wait a long time of about 10 minutes, then we start seeing some decay. Right? And we actually think this is our setup drifting, not the actual qubits relaxing. We haven't really been able to detect any relaxation. The fit here gives a T1 of about an hour. And that means that the system is really very well isolated. There's no spontaneous emission. There's no interaction with phonons in the material. You can kind of, in the ground state, entirely forget about the existence of that diamond. And what I think is really neat there is that, yeah, this means the system is very clean. The physics is really about spin-spin interactions. Right? And we'll see this can get quite complicated, because if once we have 40 spins, then this becomes it's a difficult system. But it's still, the description is still very easy. Right? It's entirely described by simple spin Hamiltonians. So one example of that is if we look at the electron spin qubit coherence. If we don't do anything, and we would just prepare the electron spin in a superposition, or like a Ramsey experiment, we just let it freely evolve, it will lose its coherence, it will dephase in about 5 microseconds. And the reason for that is that there's all these nuclear spins in the environment that make up about 1.1% of the diamond naturally. They're carbon-13 nuclear spins. And they flip-flop around, they slowly change their state. That creates a kind of varying magnetic field noise. And the electron spin picks up different phases and loses its coherence. So 5 microseconds, yeah, it's not terrible, but it's also not that long. So what can we do? We can apply a trick called spin echoes or dynamical decoupling. So we apply a train of pi pulses, Pauli X operators, that invert the spin. And this also inverts the interaction of the spin with its environment, so that the interaction cancels out. Here you can see that it works surprisingly well. So up here we prepare a superposition and it's protected. And then down here the superposition is lost. So we have dephasing. And you can see if we apply more and more pulses, starting here at 4 and then all the way up to about 10,000 or so, we can extend the coherence time to, in this case, to about 1.5 seconds. So you can really change the coherence time by almost 6 orders of magnitude by playing these kind of tricks. So that's one example of where, even though there's this quite strong interactions in the system, you can really turn them off and almost entirely. Okay, so that kind of gives us one qubit, it's electron spin. There's also a nuclear spin associated to this nitrogen atom. I have 2 qubits. How do we get more? So we have all these carbon-13 spins that are randomly placed in the environment. And what I want to show is that we can also control those as quantum bits. And the trick will be that we're going to again flip around the electron spin, just as we were doing before, but now we pick a specific frequency so it interacts selectively with individual nuclear spins in the environment. So very cartoonishly, we're going to flip that spin in order to drive kind of like a 2-qubit gate or interaction with this spin, or we're going to do this at a different kind of frequency or timing so that we can control and have kind of 2-qubit gate with that spin. Okay, I won't go through all the math for this, but I want to give you the idea of how this works. And the key idea here is really that this nuclear spin qubit evolution depends on the electron spin state. Right? The electron spin creates a little magnetic field. The nuclear spin feels this field, and that changes its evolution. So if the electron spin is in MSS0, one of the qubit states, it's like it's not there, and all the nuclear spins precess or along the magnetic field, in this case the z-axis. But then if we flip the electron spin to some other state, it creates this little dipolar magnetic field. This nuclear spin feels a slightly different field, and it precesses around a slightly tilted axis with a slightly different frequency. And now maybe you can see if I have 2 rotation axes in 3-dimensional space that do not commute. By switching between those, I can rotate anywhere in 3-dimensional space and I get complete control over the system. And because they don't commute, the order matters, and that means I can also make 2-qubit gates or entangling gates. And finally, because each of these nuclear spins has a different location relative to the electron spin, its frequency will be slightly different, and we can do this in a selective way. And what comes out of this is that if we just apply a train of these pi pulses, we protect the coherence of the electron spin qubit, and we extend it to this kind of second level, and we selectively couple it to individual nuclear spins. So the interaction is in a kind of like SZ-IX interaction, or kind of like a controlled rotation, and that you can think of both as the electron spin picking up a phase depending on the nuclear spin state. This is what we exploit when we're using this kind of as a sensor to detect where these nuclear spins are. A priori, we don't know where they are and how they couple. Or you can think of this as kind of like a C0 interaction, right, where the electron spin state controls a rotation or a flip of the nuclear spin state. Yeah, so that's a workhorse, and that's kind of the 2-qubit gate, and that's underlying all the control and everything you'll see. Okay, so we can first use this electron spin as a sensor and just see, okay, what's out there? What do we have in the environment in terms of these nuclear spins? And they're given by nature, randomly placed around. So here we do the same experiment we did before. We create a superposition, and up here it is protected. We apply 32 of these pulses. And before I was kind of showing you this envelope here. But now we look at data with much higher resolution, and we see there's a lot of stuff going on. For example, if we zoom in on the beginning here, we see that the coherence is generally protected, but there's all these sharp dips in the signal. For example, these 3, it repeats this dip signal over here. So this is now really the electron undergoing a 2-qubit gate with an individual nuclear spin in the environment. Right? It entangles and therefore loses its coherence. And that's how we detect that these other qubits are there. It's fairly easy by looking at this to distinguish that there's like about 7 of these nuclear spin qubits that you couple to. That's when we look at it or ask a PhD student to analyze this. Then we did a nice project together with the Do and Kim group, where we threw this into a machine learning algorithm and an image recognition that actually spits out then about 30 spins. And we also know that those are accurate because I'll show you later how we can do different types of measurements that can really unravel exactly what's going on in the environment. Machine learning angle is also important because each of these NV centers is going to be different. If we ever want to build a large network, this characterization better be completely computerized and automatic. Okay, so yeah, just to show you a little bit some things that you can then do. So one thing that we did is we then took one of these systems where we have 8 of these nuclear spins, the NV center, which has an electron spin qubit and also a nuclear spin qubit. And then for this 10 qubit system, we kind of showed that we could entangle all the qubits together, control them, and have a connection between all the qubits. So here you see just a case where we made all the 45 possible 2 qubit Bell states in the system. And it's important to realize that the natural connection that we're usually using if we're thinking about quantum computation is that the electron spin couples to everything. Right? It's kind of like a star. I think it's called starfish kind of configuration where there's one central qubit that couples to all the others. There's also couplings between the nuclear spins. We also use those, but they are a little bit slow to do really quantum computation. Okay, now one thing that's nice with these nuclear spins, they have even longer coherence. So here you see an example of a nuclear spin where we apply also one of these dynamical decoupling sequences. So this is up to 256 of these pi pulses. And then the coherence is extended to about a minute. Right? So these are really kind of quantum states that live on human timescales. System that I like a lot is you can also look for particular cases where you have 2 of these nuclear spins that are actually very close to each other. They couple together. They form kind of a new atom. And that has very interesting properties, forms kind of clock states, like in atomic clocks. Then you get really extremely long coherence. So here you see then the coherence time for the system, but now a T2 star. So without any of these, without any of these echoes, that's just natural kind of evolution, and that's already in the order of 2 minutes. I believe that's the longest of this kind of dephasing time for any single qubit, including ions, single ions trapped in vacuum. It's quite special because these things, if you take a piece of diamond or a piece of silicon or actually many materials, these things are just everywhere in there naturally, and they're just coherently rotating or keeping their quantum states for minutes. In this case, we're not doing anything to the diamond. Okay, then in the end, we want to build networks. How do we couple them together? I don't want to go into too much detail there, just give you the gist of it. So, take 2 of these NV centers. We hit them both with a laser pulse so that we generate a spin photon entangled state on both sides. So in this case, for example, an entangled state of the spin being in state 1 and a photon being launched early, or the spin being in state 1 and a photon being launched late. We then interfere these photons on the beam splitter. After that, we fundamentally cannot know anymore from which NV center which photon came. And that means that if we perform a measurement and we get a certain measurement outcome, that we can project the 2 spin qubits in an entangled state. Now, it's important to realize that these entanglement schemes are heralded. What does that mean? Right? They're inherently probabilistic, both because photons tend to get lost all the time, detectors are not perfect, etc. In this case, it's also linear optics, so actually the best you can do here is 50%. The other measurement outcomes are not useful. So it's inherently probabilistic, but you can just repeat it until success. And when you're successful, we know, and then we have the state and we can deterministically use it, for example, to perform stabilizer measurements over the network. Yeah, that's an important feature to make these kind of ideas scalable. As long as you have then other qubits that hold quantum states and that have kind of good memory, then you can deterministically use these entangled states in the end to perform your operations and your computations. Okay, so this works. One neat example is this experiment that we now did already quite some time ago, 2015, where we created entanglement between one NV center in a diamond here in the physics building in Delft. This is where QTIP is, and one diamond here at the other side of the campus in a nuclear reactor about 1.3 kilometers away. So this works really well. You can also do it over long distances, and that's of course specifically important for the cryptography angle. For computation, probably you want to stay away from that. Although there are also interesting aspects like blind quantum computation, where one could remotely access a quantum computer over a long distance in a quantum way. Okay, another recent experiment that I want to highlight is the case where in a group of Ron Hansson, also at QTech, they then moved on and started building larger networks. So this is an example of then a 3-node network, where entanglement is distributed over 3 of these nodes. And what I want to highlight is the importance of having multiple qubits in each node, in each little processor. Because the way this works is you create, for example, entanglement here between Charlie and Bob, and you store it in a different qubit, and then you create entanglement between Alice and Bob, and then once you have both pairs, then you use it to make a 3-qubit entangled state, or perhaps to teleport some state from Charlie to Alice, or to perform operations. Right, so this combination of multiple qubits and this herald entanglement is what allows you to build up these networks larger. Okay, so that's why we want to have actually many qubits in these nodes. And I want to show that we can control and detect many of these nuclear spin qubits. So how are we going to characterize this quantum processor, or just here simulator? I'm sorry, that's from a different talk. We're going to use the NV center and use it as a sensor again to detect these nuclear spins in an environment. But we're not going to just detect the interaction with the NV center, but we're going to measure the interactions between the nuclear spin qubits. Okay, so we measure the nuclear interactions. And these really reveal the interconnectivity of the cluster. How is everything connected? And then we can transform into the 3-dimensional structure, like where each of these qubits actually is in space. And that's a very neat kind of way to summarize our Hamiltonian here. Just the spatial coordinates of the qubits, that really gives us an accurate description of the full system Hamiltonian. Now, there's an extra motivation to this kind of work. You can also think of this as atomic scale magnetic resonance imaging. Just as you can put people in an MRI machine and make pictures of them, you could also use this to make images magnetically really on an atomic scale. So the dream there is to kind of put biological molecules, perhaps proteins, on top of a diamond, have these NV centers close to the surface, and then really detect all the individual atoms there. And in that way, create atomic resolution, single spin sensitivity, images of molecules and things like nanostructure and stuff. I won't go into that, but there's also a lot of work in that direction, and what I'll show you are also methods that can be applied in that field. Okay, so how are we going to measure these couplings between the nuclear spin qubits? Here's a pulse sequence. Don't worry too much about the details. Essentially, this first block is just a 2-qubit interaction between the electron spin and this nuclear spin that allows us to measure the state of this spin and essentially project it into some quantum state. That's how we initialize it, by measurement. And then in the end, this last block, I'm not sure you can see my pointer, but here in the last block, we measure again this nuclear spin to see what happens. In between, we let it just evolve and we apply again these trains of pi pulses. But we do this now on this spin, but also on this other spin over here. And this decouples these 2 guys from everything in their environment, but keeps the interaction between them. Right? So this makes a C phase gate between these 2 qubits. Okay, so that works. You can see that here. So in the time domain, we just see an oscillation where the spins kind of entangle and disentangle from each other. Now you can get very long coherence times. In this case, the measurement runs up to 15 seconds. And what you see here is essentially a C phase gate between these 2 qubits, but it's of course horrendously slow. Right? It's not going to be very practical to use this kind of interaction for quantum computation. The C naught here takes about a second or so. You can Fourier transform this, and then you see that we can measure this coupling, which you see here as a splitting. And we took a little bit of an extreme case here. So these 2 qubits only couple with half a hertz. And you can see we can really measure that with kind of microhertz kind of precisions, and also line widths or spectral kind of resolutions down to the millihertz. So you can very accurate measurements of all the interactions in the system in this way. then we can just sweep all the parameters, essentially to measure all the interaction between all the qubits. I'm going to go through that a little bit quick. And that gives us a kind of three-dimensional data set that encodes the composition, how many qubits are there, and how are they connected to each other. And because this is a very strongly overdetermined problem, the number of spatial coordinates are 3 per qubit. It's somewhere in three-dimensional space, x, y, z. Whereas the number of interactions that we get goes something like the square of the number of qubits. Right? It's a big interaction matrix. Means the problem is very strongly overdetermined, and we can invert this into the actual Hamiltonian or the three-dimensional structure of the system. So we run that through a computer program, and this is then kind of the coupling matrix. So this tells you that, for example, this dot here tells you that there is a fairly strong interaction between a qubit that is at this frequency and a qubit that is at this frequency down here. And in this case, we detect 27 of these spin qubits. We're measuring 171 of these couplings. We can then also show this as kind of like three-dimensional picture. So here you see the atomic scale image of this little quantum processor. You see it's pretty small. Everything here happens in about 3 by 3 by 3 nanometers. Quite high qubit density. And you can also see, so here's the nitrogen of the NV center next to the vacancy. And we really think that we can get this with very high confidence. You can do some fitting algorithms to get some ideas of uncertainties here. Here you see the 77 spatial coordinates of the system, the kind of uncertainty that we have, and it's well below the diamond bond length. So we really know on what lattice side each of these atoms is. And yeah, many of the uncertainties are really deep sub-angstrom. We get a very precise kind of characterization of this system. Okay, one nice way to show that is 3D video about this. So this is one of our what we call quantum processors that we play around with. Here you see about 3,000 atoms or so that we know the isotope of. Right, so these white balls are just carbon-12 atoms. They make up the diamond. They're boring. They don't have any spin. They're not qubits. The yellow balls are our qubits, carbon-13 spins. And then here in the middle, you saw the nitrogen, and next to that, the missing carbon atom. That's where the electronic spin is. And the hand down here gives away that this is not a rendering, but one of these nice chemical models. So this took the students, I think, a whole day to build. They also had to write a computer program to figure out how to do it, because you need some sort of instructions, right? For example, this here's Hans, one of the PhD students. Normally, he does not look this well with his hair. I think it was quite a tough day. They did this while I was in a conference instead of working. Okay, maybe an interesting question is like, how far can you push this? We're not entirely sure. We're playing around with more other kind of like spectroscopy techniques to see if you can do this further. This is kind of a preliminary result on a 45 nuclear spin system. So it's actually 47 nuclear qubits in total that we have some control over, taking the NV as well. And here you see, for example, the interaction matrix of 45 nuclear spin qubits. So we know all the 990 kind of like 2 qubit interactions in the system. Okay, so why are we excited about this? So the first thing is to use these as quantum processors as kind of the nodes of these quantum networks. And I want to be honest here, right, that controlling all this 30, 45 spins, qubits with very high fidelity is going to be difficult. Like to get all those to like 99.9% fidelities that you would really need to use them in a quantum computation kind of architecture, that's going to be difficult because this is a very complicated system, and the farther away you go from the NV center, the harder the control becomes. So for these, so there the idea is more like, let's take the closest 10, 5 to 10, and control those with very high precision. And we hope we can do that because in this system, I showed you like T1, for example, is ours. So the noise that we experience, it comes from the other spins. and we know also their properties very accurately. Right? So can we design control sequences that now control kind of the heart of this system very precisely, well, precisely decoupling it from the shell around it, which is really where our gate errors come from. Okay, that's if you think about high fidelity control for error correction and so on. The other motivation is this is a nice method for atomic scale MRI. Can we do this on things outside the diamond? Can you do this potentially on a protein that we don't know the structure of yet? That's very hard also. That's kind of a dream there. And finally, we look into using this as quantum simulators, right? So this is a nice controlled many-body physics system where we have individual control over all the qubits. We know how they all interact. We can turn interactions on and off. We can shape the Hamiltonian. Can we study interesting many-body physics with this? It's kind of quantum simulator. And there we don't really have to get to this 99.9% fidelity, right? There, the kind of like 2 qubit gates and a 99% fidelity that we have now are sufficient to get signal. I want to show you one recent example of that, where we looked into simulating what's called a discrete time crystal. So here we applied a pulse sequence that took 9 of these spins and shaped their interaction Hamiltonian so that they are effectively a one-dimensional spin chain, so a line of spins or a line of qubits that couple together. And then it's predicted that you can realize these discrete time crystals, which are a kind of like novel phase out of equilibrium phase of matter, where you have a many-body system that is periodically driven, and it then forms a stable phase where it periodically inverts itself and is robust to kind of perturbations of its Hamiltonian. That's what you can see here. So here we took these 9 spins and put them in a state where they're kind of like alternating, and then we periodically drive and invert them. And you see that this pattern inverts and repeats itself in a very stable way. And the reason for that is that due to the spin-spin interactions, there's something happening called many-body localization, or at least it's consistent with that. And that shows that even if we vary the parameters of this kind of Hamiltonian, or we drive the system in very imperfect ways, it kind of locks onto that period and forms this stable oscillating system. Okay, that's just an example. If you want to know more, the paper is down here. Okay, and so finally, yeah, let's move on to this idea of can we do some fault tolerant operations? Can we start thinking about operating on logical qubits and doing quantum error correction? So we're going to use that same system, but now we're going to only think about using up to 7 qubits that you see over here. So 5 of these carbon-13 spins and the NV center. And I first want to briefly mention an experiment that we already did quite a long time ago. So this is really old news, but I think it's nice to discuss briefly. Where we looked at a 3-qubit encoding, so the phase flip code, the smallest repetition code, distance can correct one phase flip error. And we did various things there, including doing multiple rounds of error correction and real-time feedback and so. But the experiment I want to show you is this one, where we encode a logical qubit in these 3 spins, and then we let them evolve, and we see how they decohere, how they dephase. And in between, we do or we do not do kind of rounds of error correction. Right? So we perform stabilizer measurements to detect phase flip errors. So it looks like this. The gates are a bit funny because our native gates are funny, but just think of this as measuring the XX parity of the first 2 qubits and measuring the XX parity on the second 2 qubits. Then you can get graphs like this, where as a function of time, we see the average fidelity of the qubit decay. If we now take the best individual qubit, you see that's this green line over here that has a certain coherence times. The qubits are different, so the others have shorter dephasing times. This is the best one. And then you can see here in the purple line that if we actually encode a logical qubit and let it evolve. And in the middle of it, also perform a round of this error correction to in between see did any errors occur and also fix them in real time. That quite massively outperforms the best individual qubit. That's quite interesting. Actually, it's maybe a little bit surprising it does so well, because you would expect really kind of small improvements using such a code. One reason for that is that our noise here is highly non-trivial. It's quasi-static. And that means that errors build up coherently. And so one thing that we face here is that if we actually perform a stabilizer measurement, this also projects the errors and stops them from building up. Right? So essentially, this is kind of the quantum Zeno effect on errors. If we would just rapidly measure the system all the time, then errors would never happen. That's one of the consequences of having this kind of quasi-static kind of noise of this spin environment. And yeah, one way you can see that is here, the gray line is if we actually do the error correction measurements, but we don't use the information, we just throw away anything we learn. So we don't actually correct the errors, we do only detect them and then forget about them. And you see then also we extend the coherence, and yeah, this improvement that you get here, that's kind of what you expect of actually using the information about the errors. Interesting point is also here. Here you have this crossover point. That's just because the 3 qubits are different. There are some moments where it becomes more likely that the 2 bad qubits both have an error than that the good qubit has an error. Right? So it's just best then to stop using your encoding and just measure only one of the qubits. Okay, some details. I think one thing that you might now think is like, hey, wait a minute, if this measurements can actually suppress errors, there's probably other ways to do that. And that's true, right? Like these echoes do exactly the same thing. They also cancel out this kind of like coherent buildups of errors. And we saw indeed these qubits, we can also extend this coherence time to minutes by just doing echoes. And that puts us in a bit of a weird situation in how would you interpret anything where you think about extending the lifetime of the qubit. And we run a bit into a problem there that to start with, we can kinda, if we try hard enough, probably extend the lifetime nearly to infinity in other ways. And then error correction, it's very difficult to show that it would help you. Also, in reality, you would never be idling for like hours with like long waiting times in between. Makes no sense. So yeah, I think one of the things that we learned from this is that it doesn't make so much sense for us to think about extending lifetime for qubits. Actually, and that makes sense, of course, right? Because we know that in the end, if we want to do universal quantum computation, what we care about is doing universal gates and those having exponential suppression of the errors. Okay, there's some subtleties of different noises and then what happens when you apply some error correction codes. So now let's think about can we do something that is fault tolerant? So in my kind of definitions, the previous experiment wasn't really fault tolerant, can only handle certain types of errors, phase flips on the data qubits, on the encoding qubits, not all types of errors. Okay, this would be fairly straightforward for many of you. If we want to build a large-scale quantum computer, right, we have to overcome these kind of inevitable imperfections. The way to do that is to actually operate on logical qubits, encode it over multiple physical qubits. And then one requirement that we have to hit is that all these building blocks, all the kind of gadgets that we're using, should be fault tolerant so that reliable operations become possible even with noisy elements. Now in the work publication related to this, we use definitions for fault tolerance from these papers down there. Here I'll just give you kind of a hand-waving one. Essentially, for this distance 3 codes that we're looking at, fault tolerance on this kind of lowest level, you could say it means that any single error on any of the components should not lead to a logical error. It's a little bit more subtle, and then please have a look at those papers. Okay, so lots of beautiful experiments have been done in the past. It's a lot of work on doing error detection codes, particularly a lot with superconducting qubits. In such codes, we can detect an error, but we cannot correct it. There's also been a lot of work on kind of non-fault tolerant error correction protocols that can correct some, but not all types of errors. perhaps some of these experiments are familiar to you. It's nice work with superconducting qubits, ion traps, solid state spins, mostly only with these NV centers. This is the experiment we just looked at a bit. So examples of this are kind of like repetition codes where we can detect, where we can correct only one type of error. Okay, so then there's also been experiments where people did look at fault-tolerant error correction protocols. Nice work from the Monroe group. And then a bit more recently still, these fantastic experiments by Honeywell using also trapped ions, where they could really run through multiple rounds of fault-tolerant error correction protocols. This is with trapped ions. Our question was like, can we also start getting into that kind of logical qubit and fault-tolerant space with the solid-state spin qubits? In the meantime, also some really nice work came out with superconducting qubits. Maybe you've seen the papers by ETH, Yang Wei Pan, I think also by IBM, looking at the surface code very recently with superconducting qubits. So what is the smallest possible kind of fault-tolerant operation of a logical qubit? So when I started that project, I thought it was the surface code with encoding in 9 qubits and then using one ancilla repeatedly to do the stabilizer measurements. And then in the meantime, this really beautiful work came out by Chow and Reichert, where they introduced this kind of idea of flagged error correction or flagged fault tolerance. Yeah, they show that, I presume this will be the smallest logical qubit that can be operated fault tolerant in existence, namely the 5 qubit code, and then we're using 2 ancilla qubits. And the general idea here is that if we now have these 5 qubits, we want to do this kind of 4 qubit stabilizer measurements. If we just use a single ancilla, we're going to have errors propagating from there into 2 qubit errors that cause logical errors. So that's not fault tolerant, but if we add a flag qubit that can actually detect all those cases, uniquely identify them in following up rounds of stabilizer measurements, and correct any single operation error. So that's what we set out to do. We encoded these 5 data qubits, 5 nuclear spin qubits. We use these other 2 as an ancilla and a flag qubit. And yeah, we looked at fault-tolerant encoding of that logical qubit, applying fault-tolerant gates, and then doing these stabilizer measurements with flags, which are compatible with fault-tolerant error correction. What we didn't do is the full kind of like cycle of all the stabilizer measurements you need to do for this kind of Chow and Reichert error correction scheme. For that, we still need to get to higher fidelities to make that work. Okay, I'm going to skip over this one and look at like, how do we actually then encode the logical qubit. Turned out to be quite complicated. Young Wang from the group of Barbara Terhal here came up with this scheme, which works with our kind of native gates. And you can think of this as the first 3 blocks, and also the preparation here is essentially preparing a state that is an eigenstate of 5 3-qubit operators. Right? So a 5-qubit state. If we perform the right 5 measurements, we project it into the quantum state that we want, the encoded state. That's not fault tolerant because, for example, this C0 gate here makes 2 errors. And then we get a double error here that would actually cause a logical error. But what we can now do is add these 2 verification stages here in the end, so 2 more stabilizer measurements that can then detect all those kind of errors. And important is also that here in the end, then there is this kind of flag qubit that also allows to make sure that ancilla errors in those stabilizer checks in the end cannot propagate again to logical errors. And this is in a heralded system. If these outcomes give you the right type of outcomes, then you can accept the system and you have fault tolerantly prepared the logical qubit. Get the wrong type of outcomes, we start over. Okay, so just to show you that that works. Here's a kind of like summary of the errors that come out in the end. But this is if we don't use a non-fault tolerant scheme. So the 5 qubit codes, perfect code. So any state, any number of Pauli errors can be described as either the logical state that we wanted with 0 errors, or the logical state that we wanted with 1 error, or the logical state, the opposite logical state. flipped with 0 or 1 error. And the cases on this side now are still recoverable, right? So if we apply a round of error correction, those are a single error, can still be recovered. These are the double errors and triple errors that cannot be recovered anymore. And you see that we get then a logical state fidelity of only about 81%. So in 81% of the cases, you can still recover the logical state. If you apply the fault tolerance scheme, which is more complicated, right? More operations, more qubits used, then we actually see that that becomes better. The logical fidelity goes to 95%. And kind of, yeah, neatly, one thing that you can see is that what happens is that you suppress this kind of double errors from happening by introducing this fault tolerant layer. But if it's more complicated, we actually do introduce more single qubit errors. Right? So the state that comes out has more single qubit errors, but those can still be corrected. Okay, one can then also start thinking about, can we apply some logical gate operations? I think these are not that interesting. For the 5-qubit code, one can do all the kind of Clifford operations fault tolerantly. And these are some ways to do it. So they're transversal, right? So this is Pauli X, Pauli Y, Hadamard. This is a pi over 2 rotation around the z-axis. A nice detail is that you can do this by, you actually have to shuffle the qubits around. But in our case, all the qubits coupled to the same central electron spin. Shuffling around is just relabeling, so that's also a fault tolerant operation. We don't have to do any physical swaps for that. Okay. And then finally, we can look at this kind of flag stabilizer measurement, where we now say, okay, we have encoded this state fault tolerantly, logical minus in this case, and then we want to measure this XX, Y, I, Y stabilizer, and we want to do that in a way that if any error occurred anywhere in this circuit, that the system is still recoverable. Right? So we don't actually apply all the many stabilizer measurements that come after this still, but we use the information from these measurement outcomes to kind of decode the logical qubit. Then you can see we can look at a scheme where we have this extra flag qubit that makes it fault tolerant, or we don't have it. Now, if we just run the scheme without doing anything else, then we get actually two outcomes that are very, very close to each other. And the reason for that is that these errors that propagate from the ancilla to 2-qubit errors, those are really already quite rare. Right? So the fault tolerant and the non-fault tolerant scheme here perform approximately the same within noise. What we can do is then introduce really a full error over here that in the non-fault tolerant scheme is harmful, in the fault tolerant scheme can handle it because it propagates to this flag and gets detected as well. And then you do see that if we don't have the fault tolerant scheme, this actually flips the logical qubit. So now it's more likely to be the wrong state. Whereas if we have the fault tolerant scheme, it can still recover, not perfectly because there are already a lot of errors in the system. Right? So we add another error, but in a fraction of the cases, the system recovers. Yeah, so I think there's some kind of nice first steps towards showing we can really move from this kind of operating on physical qubits with these solid state spin qubits towards operating on logical qubits and start thinking about how the ideas of fault tolerance can start helping us in the future to do better. Okay, then what is the next real important step here? Is to bring together this idea of making these photonic links together with this kind of large, very well controlled and understood quantum systems and start building networks of many nodes with many qubits per node and try to slowly edge to the point where we can start using then error correction over these networks to start suppressing errors and be able to do a larger scale quantum information processing. Okay, with that, I would want to stop. Let me just briefly mention the main people behind the last part. This kind of fault tolerant logical qubit operation. Yang Wang here from the group of Barbara Terhal, who did the theory, and Mohammed Awabai, who did the experimental part. Thank you.
you very much for that really inspiring talk. So are there any questions? Yes.
I have a couple of questions about the photonic entanglement, the heralded entanglement. Like, how long does it take to entangle things, and what's the fidelity of doing so with current?
Yeah, so the current kind of state of the art is about 40 hertz, so 40 times per second to make entanglement between two of them. And the fidelity is in the order of 90, the record is about 92%. That maybe 92% doesn't sound so high, but actually this nice work from the group of Simon Benjamin shows that that is above threshold for the service code, for example, because you are still allowed to do distillation steps, because the entanglement is just a resource, it's just something you need to prepare, it doesn't carry your actual quantum states.
So also because it's heralded, but it's trial until success. So if it fails, it doesn't destroy the state that was in the diamond. Well, you can retry, and like the state there stays the same.
Yeah, that's a very good question. So no. So actually, the entanglement process does create noise that the other qubits feel. Essentially, this electron spin undergoes some stochastic behavior. When you fail, you don't know exactly what happened, and that imprints phases on the other qubits. So that is actually what's stopping us right now to build very large networks. One way that we're working on, for example, overcoming that is to just use diamonds where the carbon-13 concentration is a bit lower. So the typical distance is a bit larger, couplings are a bit weaker, and then that goes away. And then we have shown that we can launch hundreds of thousands of these attempts while still keeping coherence on the other qubits. And that should allow us to distribute like tens or hundreds of entangled states while keeping coherence in the system. Unfortunately, for something like a service code threshold, you still need to do a factor 10 or 100 better. The idea to ultimately get there is to also make the entanglement much more faster, much more often successful, for which you have to put cavities around your defects. That improves the spin photon interface.
Was that, yeah? That's you, yep.
I have two related questions. So one, about temporal stability of your system, because the measurements need to characterize the network over 2 weeks, right? So one question. The second connected is, did you think about using some techniques like overlapping tomography or shadow tomography to perhaps faster, more efficiently characterize the network rather than directly assessing every pair?
So maybe I'll just repeat those for the Zoom audience. So first question was about temporal stability of the system, given that measurements are undertaken over weeks. The second, I guess, related question is about the use of other techniques such as shadow tomography or overlapping tomography to speed up this process.
Yeah, regarding the kind of temporal stability, yes, it's important to have that stable. I mean, one advantage that we have is that the chip itself is stable, right? It's a piece of diamond. You can put it in a closet, come back 100 years later, it will be exactly the same. These atoms don't move, they don't die. So the chip is stable. The main thing that you need stability for is the magnetic field. Right? They're spins, so they're coupled mainly to magnetic fields. So we stabilize the magnetic field to like milligauss kind of, and that's challenging, particularly because we're in a quantum computing kind of institute. So there's something like 30 dilution refrigerators with magnets around, and we can detect all of them. And then, for the shallow tomography and so, I'm not entirely sure what it is. I'm 100% sure that what we did is very dumb, right? So we measured very beautifully with like kind of amazing precision all these oscillating cosines, and then took out that information kind of by human interpretation. It must be that you can speed this up with a factor 100 or so, if you know how to teach a computer how to really look at all the data at the same time. Yeah.
Yes.
When you're running as a quantum simulator, what are the limits on the kind of Hamiltonian you can simulate?
And just to repeat, so when used as a quantum simulator, what are the limits on the Hamiltonians you can simulate?
In principle, you have universal control, right? We have this universal gate set, so you can, in principle, do anything you want, right? That's maybe a little bit not the answer you're looking for. There are, of course, things that are easier and things that are harder. So what are we really good at? What is our kind of unique selling point? Three-dimensional dipolar coupled spin systems, because that's what you get if you do nothing, right? And then you have to start shaping it. Then there's many options. Some things are easier than others, and I think one kind of challenge for us is to find out what are the problems that are particularly interesting to look at with this simulator compared to, for example, in cold atoms or so. These time crystals were one of them. Those actually are easier for kind of qubit people than for cold atom people. And I think there are more problems like that out there.
Question, Justin?
Three kind of related questions. So I assume you only choose one NV center per crystal, and if so, then what are your criteria for choosing the distributions of which NV center specifically you want to choose, and what are like some unfavorable NV centers? Like, okay, this one will be useless, and why, basically.
So the question was, if you choose one NV center per crystal, what's the criteria for choosing that?
Yeah, at the moment we choose one per crystal, but for the kind of like more scalable networks where we want to have many of these nodes, we are working on putting many nodes on one chip, right? So one diamond containing many NV centers or other defects. So it's not limited to one per diamond, per device.
The third question would have been, how do these crosstalk if they're in the same diamond, or are they completely isolated or insulated?
Then that becomes a challenge, yeah. The nice thing is that you can, that any crosstalk, you can, if you want, go to the case where every qubit is separated by a meter, and then you have no crosstalk, and you can find a sweet spot somewhere. You have flexibility. That's a nice thing there. The other thing, how do we select the NV centers? Actually, not that much. There's some boring things like the orientation and so. But to give you an idea for the carbon nuclear environment and all that, this is just the first NV center that we took. Right? We just took one and did all those experiments. We think you can do this virtually on any NV center. They're all going to be unique. It's all going to be different, but right?
Yeah.
But because we're in fairly high number space, we're looking at a piece of like 4,000 atoms where it's like 40 of these qubits in there. Those are going to be distributed differently, but practically it will have similar kind of properties because it's already kind of like a Gaussian around some point, some small standard deviation.
So I think maybe if there are no more questions, I might ask a question, if that's okay. So if we imagine an algorithms or software developer using your quantum processor, what sort of interface are you imagining sort of providing to them? I mean, would we expect them to be, thinking, okay, I'm going to do a CNOT gate or whatever, or would they be working at a different level, lower level maybe?
Yeah, it's a good question. So currently the system does already generally work also for the students on a level, right, where you say, yeah, perform 4 qubit parity measurement on those 4 qubits, then measure that parity or whatever, right? And it compiles that automatically in all the timings and so. This contains, the sequence I showed you contain actually thousands of operations that are all timed, and it's a nasty computation, but it's done automatically. I think where we would like to work to is two things. On the one hand, where you can use them as for quantum algorithms, right, where you can just have kind of gate level control. I think the other interesting one is to think about, can you do something where you can say, like, I want this Hamiltonian in a simulator, and that then the system figures out itself how to smartly generate that. That we don't have yet. There is a big project within QTech called Quantum Inspire, which is a little bit similar to the kind of IBM quantum experience, where there is a large kind of full stack engineering development also to provide that interface essentially.
Thank you. Okay, so let's thank Tim again for a really inspiring talk.